All right, so in this video, I'm actually going to go ahead and we are going to look at a conducting wire in a magnetic field. So far we've just been talking about charges moving through a uniform magnetic field. But if I place a conducting wire into a uniform magnetic field, we'll just use the same one, there's also going to be a force acting upon it. So here's my conducting wire, and there's some current traveling through the wire. Now, we can use our right-hand rule to figure out the direction of that force, okay? But the one thing that we have to remember is the idea that when I have a current going in this direction, it's actually meaning that the electrons are flowing in the opposite direction. And for my second right-hand rule, when I'm looking at force, my thumb points where the charge is going, so the velocity of the charge flow. So let's just go ahead and do this. So I've got an electron moving down. I'm kind of using the same example every time, so it kind of hits home. So I've got my thumb moving down with the direction of the charge, my fingers pointing in, and it's electrons flowing through that conducting wire. So the direction of the force is going to be through the top of my hand. So there would be a magnetic force on this wire in the magnetic field. Now, there is a way of calculating this since we don't just have one charge, we have a full current. And there is a length of the wire that is contained within the magnetic field. Okay, so the longer the wire, the shorter the wire, the more of the force it's going to be experiencing. So the equation for calculating magnetic force on a conducting wire within a field is equal to BIL, where B is the magnetic field, I is the amount of current, and L is the length of the wire. Now, there's also this sine of theta there, and that's to take into consideration that they should be perfectly perpendicular. If you arc this a little bit, or you arc the magnetic field, and they're not perpendicular with one another, it's actually going to decrease the force, okay? But if they're perfectly in this like perpendicular scenario, which happens in most instances, then the sine of 90 is just 1, and this really isn't going to affect your answer. Now, let me just do a quick example of what happens then if we have two charges next to each other, or two wires next to each other. So using the first right-hand rule that we've learned, let's say this current's going up, and let's say this current's also going up. And then I'll do an example down here where I have one current going up and another one going in the opposite direction. Let's see what happens with the forces. So here we're going to use the first right-hand rule to see sort of what magnetic field this guy over here is experiencing as a result of that one. And I'll actually use a different color marker so we can distinguish, right? So again, this is going to be the first right-hand rule. So first right-hand rule, we're curving around a wire to determine the magnetic field. So over here, if I'm going to point my thumb in the direction of the current, and over here, where this wire is located, there is going to be a downward magnetic field that this guy is in, right? As a result of this guy's current. So we can then use our second right-hand rule to figure out the force. So this is just the same scenario as I've been looking at every time. Fingers in, thumb down, because electrons are moving this way if current's moving up, and again the force on the wire is going to be in this direction. So there's going to be a force magnetic in this direction, right? Now let's look at it in terms of what this wire then is doing to this wire. So here I'm going to go back to my first right-hand rule where my current is going, and you can see in this direction and over here it's coming up out of the page. And so this fella is experiencing a force up out of the page, right, as a result of this guy, okay, because of here. And so then let's think about the force that's acting on him, right? So again, I'm going to point my thumb in the direction of where the electrons are going, which would be down in this case. But now my fingers are pointing upwards because it's coming up out of the page. And I know that's horrible to see. But again, electrons are flowing, so it's attracted to the positive side of my hand. And so there's a force on this wire as a result of him in this direction. So when the currents are going in the same direction, those wires are actually going to attract one another. Okay? Now, let's do the opposite scenario. So now I've flipped it upside down. This guy's still experiencing a force like this, or excuse me, experiencing a magnetic field like this because of this. Now let's look at the force. My fingers are now going to point, my thumb is now going to point upwards opposite the current, and my finger's in, so the electrons are going to be attracted and be moving to the right in this case. And then oppositely, if I have my thumb pointing down here, we can see over here, this is going to be into the page on this side, so the opposite of that because my current has flipped. And then back to the second right-hand rule where I'm looking at force. My thumb is pointing down, and my, I'm sorry, you can't really see it. My thumb's pointing down, my fingers are pointing in, and therefore the electrons in that wire are going to have a force acting towards the top of my hand, which would be over here. And so in this case, these wires would repel one another. So when the two current carrying wires have current going the same direction, they are attracted by a magnetic force, and here on the bottom they are repelled because the current is going in the opposite direction.